Well, hello. It's that time of year, final exam. Semester went by really quickly. I had a great time teaching this class. And you, my student, did a great job. You were awesome. I'm proud of you guys. And it comes down to this weekend. Put some time and effort into it and give it a best shot. I'm going to go over a few problems. And pay attention exactly what I say. It will pay dividends. Just put effort into it. All right, let's start with this problem first. This is we got a rigid piece of pipe or beam here, and it's supported by a guy wire right there. And the guy wire has a diameter of 1/4 inch, 0.25. It's made from 836 steel. Well, we know a lot of property about that. And it has a load P at the end of it. And the question is, what kind of load, if we put a load up here, and the displacement because of this load is 0.15 inch, then how much load it is, and let's calculate that, and figure out also we can calculate if the wire can break or not break. And what I did here, I just did a free body diagram and taken this, and there's my load P. And 3 feet away, there's my guide wire, which is going to this direction. We call them FBD. And the angle for it, this is 4 feet, this is 3 feet. And you can also figure this out, and that become 3 squared. You know that, right? So let's figure this comes out to right here. 4 squared plus 3 squared, square root of it, it's 9, 16, 25, 5. So it comes out to 5. So this comes out to 5. And therefore there is your 5 right here. Okay, so we good on that. And now we want to figure out, take a moment about point B. That way we can calculate what these forces are. All right, I'm going over here. Summation moment about point A is equal 0. Always make a sign for yourself, say counterclockwise is positive, and therefore so this is how the two, this force right here can be break down to 2 segments, right? It's going to be a vertical segment of it and horizontal segment of it. We don't care about this X segment because it's going to be 0, so we care about the vertical segment, and that comes out to what? Remember, this is 4, 3. So if I'm going to say, okay, that's a 4 over 5, so become 4 divided by 5 of FBD. All right, now that's what become right here. 4 over 5 FBD, and multiply by 3, right? And that's a positive. Then minus P times 6 is equal 0. And if you simplify that, which I have, comes out to FBD is equal 2.5 of P. Good enough. One thing we have to notice here is this is deflecting by 0.15 inch. Let's exaggerate this. Actually, you know what? I need to erase this stuff here a little bit so I can have room. All right. Say this is a beam comes down by exaggerating it. And this is a 0.15. Therefore, I'm really more concerned about right here. Okay, so this right here. So what am I saying here is that cable, it's going to stretch. If this is going to come down 0.15 inch here, so this cable is going to stretch from here. See if I can make a straight line, which I can, but aha, use this. Great. All right. We're cooking. So now the new cable based on this load, it stretches up like here. Now I'm going to end up with this triangle. And if you take a look on the screen, was last semester actually, we talked about cosine law. And based on cosine law, we can go ahead and figure out the length of these cable, how much it has stretched. First, let's figure out this angle here. So now let me redo that. We have that cable going like this, all right? We've got to figure this angle out, and then we know this angle, right, is 90 degrees right here. So I got 90 plus this angle. What do we know? This angle is sine alpha. If you call this alpha, sine alpha came out to 4/5. And if you can, then alpha comes out to 53.13. And therefore, this angle right here, I'm looking for the total angle, which is, let me use a different color. That'll be fine. This angle right here, and that comes out to 90 plus 53. That makes it 143.13. All right. Now I know that, and then I can use cosine law to figure it out. So using cosine law, we end up with this length, which we call LB prime, LBD prime. So that's a D. This point will be D prime, okay? LBD prime. So I got LBD prime is equal, using a cosine line, I have this came out to 5 feet. If this is 4 feet, this is 3 feet. That came out 5 feet, so 60 inches, right? 60 inches, okay? And then plus, what is this here? This length right here is half of that. So this length right here, that's a 0.075. Because if this is 0.15 here, halfway through it become 0.075. So this part of the triangle is 0.075, and this part of the triangle is 60. And the cosine law says, okay, this square plus this square minus the 2-time angle between them. Okay, we're good. So plus 0.0, whoops, that's a square here, 0.075 squared minus 2 times 60 times 0.075 and time cosine 143.13. Okay, so you calculate that, comes out to LBT prime comes out to 60.06. Okay, so now I have that. Then what? Of course, we have a bunch of formula we can use, and we can figure that out. You remember that strain was, let me write it here. Okay, it was the final length minus initial length divided by initial length. So our initial length over here is 60 inches. Our final length is 60.06. So divide that out and comes out to 60. So that comes out to equal 60.06 minus 60 divided by 60. And my E comes out to, strain comes out to 1.003 times 10 by -3. And that's what we usually call inch per inch, right? So now I have figured that out, so we know that. The next thing we're going to find out is the stress. The stress is equal module of elasticity time strain, and this is the A36 steel, so we have all that information, and that's 29 times 10 by power 3, right? So which is equal 29 10 by power 3 KSI time 1.003 times 10 by power 3. That comes out to 29.01. And that's less than A36 steel, so less than 36 KSI. We got that there. So we know it's not going to break. Need a room. Let me see if I can do it right here. Stress BD is equal FBD divided by the area of that cable, which comes out to, and we said FBD is 2.5 P, and divide that by the area was pi divided by 4 1/4 inch, right? Squared. So that's equal 29. That's the stress we have, so we're going to use 29.01. Therefore, all I have unknown is here, and my P comes out to 570 pounds. Your test. Let's look at this problem first here. This is a cantilever problem. We have a uniform loaded of 2 kips per foot, and then also we have a concentrated load of 4 kips. The beam is about 10 feet long and is W24 by 104 A36 steel. And we're going to use a method of superposition to calculate the deflection of this beam due to these 2 loads combined. When we use a method of superposition, we talked about going to the back of the book, and there are different shapes in Appendix D, as you can see on the screen, and we can go ahead and subdivide this to 2 different type of loading. So I can say, all right, this is equal to, and bring the same beam down. This time I'm just gonna, it's right here, just use the distributor load on it. So this beam is equal that, which kind of deflects like this, you know, and we want to see what this comes out to. Let's call that V of W, and we're going to calculate that by superposition. We're going to go ahead and look at the back of the book. Then that's equal that plus, don't forget this, same beam, this time only using a concentrated load, which was right here, and this was 4 kips, and this is here 2 kips per foot. All right, and this going to deflect the same way. And we want to find out this deflection. Let's call that V of P for concentrated load. Now take a look at the screen, what's on screen, and if we look at the book, Appendix B, we find out that the the V, the deflection due to the uniform load is W, let me write it down here, V to the W load is equal WL4 divided by 8EI, and that's in X direction. And we can calculate that simply. We know it was 2 kips per foot multiplied by 10 by power 4, divide that by 8EIX. That comes out to 2,500 kips cubic feet, and divide that by EIX. All right. Again, going back on the same screen, we can see that the deflection due to concentrated load is going to come out to, let's call it VAP, PL cube divided by 3EI in X direction. And that's going to be 4 kips times 10 by power 3 divided by 3EIX. And comes out to 1333.33, same unit, cubic feet, and divided by EIX. Now the total deflection for this is going to be these two combined. So we're going to say V is equal V1 plus V2, let's call it V1 V2, or VAP VW, which is equal 2,500 plus 1333.3, divide the whole thing by E. E for this steel, if you look at the section over here, what I put on the board, it's a 29 times 10 by power 3 KSI, and then we have the moment inertia comes out to 3,100. And the total that comes out to total deflection comes out to 0.0737 inch. Let's fix that, make it an inch. There you go. Let's review this one more time. We have a load, distributor load and a concentrator load in a cantilever as shown. 2 kips per foot distributor load, and concentrator load as 4 kips here. So we're going to use a method of superposition. What do you mean? We're going to go ahead and break down these two different shape, and then we already, for shape like this, the deflection has already been figured out. So you're going to reuse that. Then if you go to Appendix D and look at these, we can find out, all right, I can break down this to two different shapes just alone by itself using the uniform load, which is right here, and that has a certain deflection based on that. Then I would due to a concentrated load. So now once you have that, you're going to add these two up together, and we find out the total result. There's another problem here. We got a wooden beam, and the span is 1.2 meter, and we got a force. We don't know what it is. At the middle, it's going to be P, and we'd like to know how much that force is given the allowable stress for that wood is 8.5 megapascal, and the shear max is 0.8 megapascal. And if you look at the cross section of the beam, you see it's a rectangular, and it's 140 by 240. And you gotta think about this. We're gonna solve this problem, figure out P. But what if I knew P and I didn't know this? It's the same way, same method. Okay? Pay attention. Good. One thing you want to do, let's start out with the shear moment diagram, because when you design a beam, you really want to know what is your maximum moment, what is your maximum shear. I mean, in here, we can just figure it out by calculations. Okay, my maximum, I can figure the reaction out, but it helps you to do a shear moment diagram. It will make it more defined. That's my recommendation. Let's figure out the reaction. Now, the reaction we know obviously is going to be P over 2 on both sides, but how we do that? If I take a moment, if I call this point A and call this B, let's take a moment about B. Okay, your sign says going counterclockwise is positive, and therefore if I look at this, I will have it'd be like here. I have a load here in the middle, and I have a reaction force on both ends, and then my distance are 0.6, 0.6, and that's a free body diagram. So I'm going to have, let's call this AY. It become AY times 1.2, and that's going to be negative, and plus P times 0.6 is equal 0. And therefore, AY is equal P over 2, and if you do summation of F of Y is equal 0, and that will give you P of Y is equal P over 2. All right, I want to do a shear moment diagram. Just for that, let's bring this all the way down. And make a line here, and a line here for a moment. Yeah, this color is good. So we said P came out to P over 2, so this is going to be P over 2, and nothing going to happen, come all the way here. So this is P over 2, all right? And then it's dropped down by P. It's going to come here, and nothing happened until we get to the other side. Perfect. And then the reaction here says P over 2. It's going to go back to here. This is your positive territory. This is your negative territory. And this is P over 2, and this is P over 2. All right? That's my shear, right? Now, I can tell you my Vmax right away is what? P divided by 2. Now, let's do moment. This is positive, okay? If you integrate this, if this is a constant, it's going to have a linear. So if that's there, and therefore I'm going to pause if I'm going up from here. There. Now this is negative territory. I'm going to come back down to 0 here. Perfect. So this is my moment. What is the magnitude of this moment right there? It's the area here. So it's going to be P over 2. My maximum moment comes out to P divided by 2. It's the area of this portion here, and divided times 6, right, 0.6. All right, so that becomes 0.3 P. That's your maximum moment. Now you know two good valuable information. You got your maximum shear, you got your maximum moment. So no matter how this problem is presented to you, whether you have P and you don't know this dimension, this is the method. Use the same method. You figure out your maximum moment, you figure out your maximum shear. Then, for a shape like this, the section module is S is equal, let me use a different color so you can know this. All right, is BD squared divided by 6. Or BH squared in this case. BH squared divided by 6. And this will be your B, and this will be your H here. Okay? So now you have this, and you plug in for that section modules, and it become 0.14 multiplied by 0.24 squared divided by 6. And S comes out to, what do I have? 0.001344 cubic meter. All right, now what's the stress equal to? Stress is equal MC over I, or M divided by S Okay, so we know that's 8.5. So this comes out to, where was my max? 0.3p. So, and maximum stress was 8.5. 8.5 megapascal. What's megapascal? It's 8.5 times million times Newton per meter squared. And maximum moment came out to 0.3p. And divided by 0.001344. And when you calculate that, watch out for your unit. P comes out to 38.08 kilonewton. All right, so what we did, we used the stress. We know the stress is equal to MC over I, or M over SX, and this way we found out P. But that's one way. The second way, we're going to use the shear. See what if we use the shear, what happened? You worry about those two different things. So the shear came out to, let's do it this way. Shear is, what's the formula for shear for a wooden block like that? It'd be 3 over 2V, right? 3 over 2V divided by A. And that comes out to, and we know 0.8 megapascal, which is equal to 3 times maximum shear came out to P over 2, and divided by 2 times the area, and the area is 0.24 times 0.14, and that's equal 0.8 MPa megapascal. So now we find out P comes out to 35.8 kilonewton. Now, the problem is wooden block. We know the dimension of the block. What if you didn't know the dimension of the block? Same procedure. Good luck to you.